So once again, good morning everyone, and this is lecture number 6. And we are going to deal with something which is very fascinating and very easy to understand, and that's known as the Doppler's effect. Now, basically, we see Doppler's effect in any type of wave. Here we are going to deal with two specific waves, and those are sound waves and light waves. Doppler effect in light wave is probably not a part of your course, but we'll just go through this anyways. Doppler effect in sound is definitely a part of your course, and again, I'm expecting a numerical on this. Basically, theory from the other part, but maybe a numerical from this one. So, without wasting any further time, let us jump into this topic, which is very small, very short, but very good, and it has an everlasting effect on your memories that you understand what is happening. Doppler's effect. Now, what is this Doppler effect? You must be having some understanding of this topic. You might have heard this term before. If you are an observer and you hear, see, this sound is coming from the fan, but this fan is stationary. You are standing on the roadside and you hear the sound of a vehicle passing by. Now, it's very simple to understand that if that vehicle is producing some sound, obviously it will be producing some sound because of the machinery and all that. Let us say it is pressing its horn so that you hear one constant sound. When the vehicle is far off, the frequency which you hear of the sound is different. When the vehicle comes closer, the frequency becomes different. When the vehicle leaves you and it goes away, the frequency also changes. This apparent change, actually the vehicle is still pressing the horn. He has not changed his frequency, but the frequency that I as an observer hear changes. This phenomena is known as Doppler's effect. The apparent change in frequency is not a real change because frequency has not changed. The apparent change in frequency or wavelength observed by an observer due to relative motion between the source and the observer. Source is the object that is producing the sound. Observer is the person who is hearing this sound. The apparent change in frequency because of relative motion between the source and the observer is known as Doppler effect. It takes place in both sound and light. In sound, it depends on whether the source or the observer or both are in motion. Whereas in light, it depends only on the fact that whether the distance between the source and observer is decreasing or increasing. So remember, slight difference between Doppler's effect of sound and Doppler effect of light. In sound, we can have the source moving, we can have the observer moving, or we can have both moving. Different. But in case of light, it's not the case of who is moving, it's only the case of whether the distance between the source and the observer is increasing or the distance is decreasing. You might see on a clear sky, definitely not in Hyderabad. You hardly see any stars there, too much light. Go to your villages, see clear stars. And then you see some stars are looking red. That is known as red shift. Have you seen some stars just looking like red? We'll see how that star starts to look red or blue or whatever. That is Doppler effect in light. Doppler effect in sound. You're in Hyderabad, you will hear a lot of Doppler effect of sound. I'll give you a minute to note this basic definition down. Then let's move ahead and quickly write down what are the conditions when Doppler effect is observed for sound waves. Right? And have different scenarios. The source is in motion, observer is rest. Observer is in motion, source is at rest. When both the source and observer are moving with unequal velocities, remember, if they are moving in the same direction with the same velocity, there is no relative motion. So basically what it is saying is that there must be relative motion between the source and the observer. Do we understand this? So if both are moving, it is not said that there is motion between the source and the observer. It is said that there is relative motion between the source and the observer. So source and the observer both moving does not make sense. With the same velocity does not make sense. If they're moving with unequal velocities, then only you will have Doppler effect coming in. Then you have the medium itself. A huge wind is blowing. But if only wind is blowing and the source and the observer are not moving, you will not observe any Doppler effect. But if there is relative motion between the source and the observer, at the same time wind is also blowing, then you will have Doppler's effect. Do we understand this? You must remember this. What are the limitations of Doppler effect? The velocity of sound should be the velocity of source should be less than the velocity of sound. If the velocity of source is too high, then you have shock waves. When you have someone breaking the sound barrier, moving faster than sound, jet planes do move faster than sound. Will not observe any Doppler effect because of this plane moving so fast. It will generate shock waves, and your Doppler effect must be lost, would be lost. Similarly, your observer should be moving with a velocity much less compared to the velocity of light. Do we understand this? Yes or no? I'll give you a minute to note it down. Then let us also mark those cases where you will not observe any Doppler effect. Some points may be common. When the source and the observer both are at rest, there is no Doppler effect. If they are moving with the same velocity, when I say same velocity, it also implies same direction, no Doppler effect is observed. Third case, which was not discussed there, when the velocity of the source and the observer are in mutually perpendicular direction. One is moving here, one is moving here, perpendicular. You will not observe any Doppler effect. If the medium only is moving, strong wind is blowing, source is stationary, observer is stationary, but a wind is blowing, no Doppler effect. The other way of saying it is when the distance between the source and the observer is constant. So there must be change in distance. This change in distance can be brought by only source moving. This change in distance can be brought by only observer moving. This change in distance can be brought by both of them moving, but it cannot be brought by only the medium moving, source and observer moving within the same direction with the same speed, or only the medium moving. Do we understand this? Can I have raised hands from all of you that we understand this? I'll give you a minute to note it down. A minute, 2 minutes. Let's move ahead and see the case, different cases, and you will write the heading and you'll have to probably draw the diagram. If you have time, draw the diagram. So the first case is case number 1. Source is in motion. Remember, observer is at rest. As you can see here, source is moving, but the observer is stationary. Do we see this? Can I have some raised hand that we understand this? Okay. So what happens when the source is moving towards the observer? The wavelength of the sound that you hear, remember, speed cannot change because the medium does not change. The only two things that are going to change is frequency and wavelength. Do we understand this? Here, the distance is decreasing, so the wavelength decreases. and therefore the frequency will increase. Do we understand this? Here, frequency increases because wavelength decreases. Wavelength decreases, you can remember it. Distance is decreasing. Do we understand this? Well, the frequency that is heard by the observer is n dash. You can see n dash. This n dash, and you have to remember this formula. This n dash is equal to n divided by v minus vs, where v. What is v? V is the velocity of sound. V is the velocity of sound, and vs is the velocity of source. Do we understand this? Can we remember this case and note it down in your sheets? I'll give you a couple of minutes to do that. Then we must go ahead and understand the next case. In the next case, what is going to happen? In the first case, the source was moving towards the observer. So what is going to happen in the second case? Tell me. First case, source, this is observer, this is the source. Source is moving towards the observer. In second case, what is going to happen? This is the observer, this is the source. What will happen now?
Observer towards source.
Ah, abhi source is only moving, yaar. In first case, source is moving towards the observer. What will happen in the second case? Think again. Observer, source. First case, source is moving towards the observer. What will happen in the second case? The source will move away from the observer. Remember, we are only dealing with cases where source is moving and observer is stationary. Remember the main heading that I told you. Source is moving, observer is stationary. In first case, source is moving towards the observer. In this case, source is moving away from the observer. You can think it of this way. The distance increases, therefore the wavelength increases. You can see the wavelength increasing. So the frequency will decrease. So remember this. Frequency will decrease and wavelength will increase. Vs is the velocity of source, v is the velocity of sound, n dash is the frequency heard by the observer and becomes n into v divided by v plus vs. Do we understand this? Yes or no? No, yes.
Understood, sir.
Well done. The apparent wavelength will be given by this formula. It is ulta of the formula of frequency. Do we see this ulta of the formula of frequency? Yes or no? No or yes?
Yes, sir.
I'll give you 2 minutes to note it down. Remember the case where we are only dealing with case where the source is moving. In case number 1, source was moving towards the observer. In case number 2, source is moving away from the observer. I'll give you a minute to note it down. Well then, what we have seen in Doppler's effect today is what happens when the source is moving. We have seen 2 cases. In case number 1, source was moving towards the observer. We have seen that the wavelength decreases and frequency increases. The formula is for frequency, original frequency into V divided by V minus Vs. Wavelength will decrease, frequency will increase. In second case, observer, source is moving away from the observer. Wavelength decreases, but wavelength increases, but frequency in this case decreases. I hope we have understood this. In the next class, that is tomorrow, we are going to do the next 2 cases. What will happen in the next 2 cases? Tell me what is going to happen tomorrow. Which 2 cases are we going to do? Tell me. Now, in the next class, the source will remain stationary and the observer will start to move. Do we understand this? And then in the last case, both the source and the observer would be moving. This is the way we are going to proceed. So I'll see you in the next class, in the next lecture. Till then, have a nice day and may God bless you all. Take care, beta.